who is the Chief Engineer for Scalability. This is our 5th generation pod we are going to showcase you. Uh, we will describe all the systems we have already implemented on our pod and all the things we are currently in development stage, which we are planning to implement on our future pods. To describe a few things about our team comprises of 76 members, all of whom are students in IIT Madras, and our team work puts their best foot forward, even though we all are a student team and work part-time. Our team comes from a diverse fields of engineering, from mechanical engineering to electronics, and in like our team started in 2017, and in past 6 years we were able to gain a lot of accolades. First one being the winning the most scalable award in 2021 European Hyperloop Week. Further, we have been developing our pod technology for last few years, and we have also started to develop infrastructure for the Hyperloop technology. Uh, our current goals, which we have taken for our team, is to establish a 500-meter Hyperloop testing facility in India, which will be the largest testing facility for Hyperloop technologies all over the world, run by a student team. Sorry, yeah. I would like to describe more about the pod technologies which we have implemented on a pod. Uh, we have displayed how we can do the contactless propulsion and contactless braking. We have batteries on our pod integrated to power all the system. We have control boards, inverters, and DC-DC converters to power levitation system. We have pneumatic actuation for our eddy current braking system and suspension component for different cases. To describe general specifications of a pod is designed to operate roughly at a top speed of 120 km per hour, having a weight of 370 kgs. To describe more technologies which we are currently working on, we have demonstrated 1 degree motion levitation setup, and we are integrating this levitation setup on our pod. Further, as we have already showcased the contactless braking and contactless propulsion, we are expanding their capabilities to include regenerative braking in the same setup. I would like to hand over to Prakar to describe more in details about the subsystems we have.
Great. Thanks, Ankit, for the amazing introduction. So yeah, I'll quickly walk you through the electrical and the electromagnetic subsystems. So starting off with traction, uh, we there's some echo from somewhere. All right. Anyway, so carrying on. Yeah. So what we use for propulsion is the linear induction motor. Uh, we have an aluminum rail, as you can see over here, the aluminum rail in the center, and then two LIMs on either side. So the thickness of the aluminum rail is 6 mm. And the reason why we go ahead with a double-sided LIM system and not a single one is so that we can decouple the levitation forces from the propulsion ones. And also another reason is to reduce the infrastructure cost. So, there's cost associated with the permanent magnets and the track design. So by using an LIM setup, we eliminate those costs as well. So if you can see, there are certain parameters at the bottom right, which is the number of turns per coil and the number of parallel turns. So the way we had calculated these parameters was we first had our force requirements and geometric constraints given by the pod design. And then based on the literature research and the ANSYS Maxwell simulations that we did, we decided that, having 32 turns per coil will be the ideal way to go ahead. So, and this entire system, the difference between the distance between the LIM and the aluminum rail is 4 mm. That's what we maintain it at. Yeah, we can move to the next slide. Yeah, so talking about the simulations, all these simulations were done in ANSYS Maxwell. What you see over here is the force versus speed curve operating at different frequencies. Our goal was to obtain a 1 kilonewton force, which we achieved, as you can see in the first three curves. And from simulations, we have achieved that. We've figured out that our LIM can work at an efficiency of 70%. What this means is that we can get our 300 kg pod to go from 0 kilometers per hour to 130 kilometers per hour in just 200 meters. So yeah, we can move to the next slide. All right. So talking about braking, as Ankit had already mentioned, we use pneumatics to power our brakes. The braking is completely contactless using eddy currents. We use permanent magnets, which are arranged in a Hallback array. So what the Hallback array does is that it concentrates the magnetic field on one side of the setup while almost nullifying it on the other. So because of that, and the brakes remain in an actuated position naturally, and only when we power them up, they go into the retracted state. That is purely from a safety point of view. Yeah, we can move ahead. All right, so talking about the guidance systems, that is levitation, we use electromagnetic suspension, that is EMS for short. So we have 4 EMS coils on all 4 corners of the pod. These 4 are independently controlled by 2 AC/DC chopper units. Each unit will control 2 EMS modules. So we can move to the next slide. Yeah, so in equilibrium, that is when the pod is actively levitating, it will have a current of 15 amperes passing through it. Okay, and the equilibrium air gap will be 6 mm. So if you can see over here, we have the F track system. The shape of the track was again decided by using simulations. So we realized that this is the best shape to make the most use of the flux and the force that we could obtain. So we went ahead with the 6 mm air gap and an equilibrium current of 15 amperes for each EMS. This being an inherently unstable system, we need an active controller, and we use a decentralized PID controller for that. Yeah, we can go to the next slide. Okay, so to give you a brief overview of the embedded systems, it ensures the smooth control of the pod and takes care of fault situations. So a general pod run starts off with everything off, that is the primary pack, the secondary, inverter, levitation, propulsion, everything off. And then, it slowly moves from state 1, state 0 to state 1, state 2, state 3, following this entire diagram. In the interest of time, I will not get into the specifics of this diagram that you see over here, but a basic overview is that if everything is successful, it will go from 0, 1, 2, 3, 4, all the way to 8. If there is a fault, it will go to one of these states, and then based on the data, it will be redirected to the appropriate state. So that's how it works. The next slide. Yeah, so this the PCB is the hardware which collects the data and ensures that this the state diagram that we saw above is implemented properly. We use a potenta for data acquisition, and the state diagram runs on this. Yeah, so the next slide. So this is the graphical user interface, or the GUI. All the data which is collected on the pod is sent to the base station, which is then displayed on the GUI. I'll just come back in a second. Yeah, I'm so sorry for the interruption. So yeah, coming back, the GUI, it collects all the information and sends it to the base station, which is then displayed over here. We also use the GUI to, control the pod, to give it signals and determine its state. The GUI is completely in-house design, and it runs on Node.js. We can move to the next slide. So the control strategy, this is basically how the code is structured. So in the beginning, all the variables are initialized. Then in the next stage, data acquisition happens. That is, data is collected and given to the code. Then data processing, all the data that is collected, it is processed and actions are taken based on that. If there's any error, it goes into the relevant fault state as per the diagram shown earlier. And that's how the loop is completed. Okay, so coming to high power systems, to give you a brief overview, we have two battery packs, one primary, one secondary. Primary for the high voltage supply and secondary for low voltage. The primary battery pack powers the inverter and the DC-DC converter. Inverter is used for propulsion, DC-DC converter for levitation. The secondary pack powers the control units, the respective control units, propulsion and levitation. All right, next slide. Yes. So quickly explaining about the battery packs. We have two, as I just mentioned, one high voltage, one low voltage. Both these battery packs are completely in-house designed. We procure the cells and then everything surrounding that, that is the casing, the holders, the bus bars, they were all designed and manufactured by us. For the primary battery pack, we use a state-of-the-art lithium balance BMS, and the cell interconnections are laser welded. Whereas for the secondary battery pack, the cell interconnections are wire bonded. Yeah, we can next slide. Okay, so talking about the control units. On the left, we have the propulsion control unit, which is the inverter. So the specifications are as shown over here. Hardware, the control algorithm that we use is V by F, and the hardware is easily scalable to implement vector control in the future. On the right side, you see the DC-DC converter. We use the H-bridge configuration for this, where IGBTs are used for switching, and the F2A3790 launchpad from TI is used for data processing. Yeah, that's it. So yeah, now I'll pass it on to Ankit for explaining the mechanical systems.
Yeah, coming to, can you hear me? Can you hear me?
Yes, we can.
Yeah. Okay, coming to suspension side. So I will first like to describe the lateral linkage, which is there to ensure there's no yaw movement in the system. The lateral linkage, you can see the image on the right hand side. This linkage has a spherical wheel to ensure it can move up and down, and also the forward motion is allowed. This up and down movement is needed as there might be some deviation in the track and the levitation system has to adjust for it. And this ball spherical wheel allows for this motion. This system is made using a class 2 lever with a spring and damper arrangement. Further, we have also implemented a vertical suspension system, which is a system which is implemented only in case there's a failure of electromagnetic suspension. It is based on the bell crank mechanism with a spring and damper system. Further, we have also implemented a first point of contact system. In case all our system fails, we have to ensure a braking system and propulsion system do not get damaged or damage the track. So this component is the first thing which is going to touch the track, and all the forces will be transferred to this. Coming to the chassis side, I'll first like to describe the choice of material we have taken. We have designed a chassis using aluminum 6061. A general material people use is composite material like carbon fiber and fiberglass. But in consideration of scalability, our major aim was to reduce the cost. And by using 6061, the cost which we got is a fraction of what we could have got using a composite material. This chassis integrates all other components ranging from holder for braking and LIM. We have done extensive simulations on the chassis by considering remote forces and remote loads from all the components, and we have ensured the maximum amount of deformation we are getting is 2 millimeter, and the maximum amount of deformation critical zones are less than 1.5 millimeter. We were able to achieve a weight of less than 45 kg for the entire system, and this chassis, because it's made by cutting aluminum sheet using water jet and then welding, is less than 1,900 euros. Now I would like to describe about aerodynamics. Aerodynamics is essential because while running, the pod will face some aerodynamic drag even if it's running in vacuum system. We have designed a shell which has a drag coefficient of less than 0.085. This ensures the total drag force always remains below 15 Newton. Further, the shell is manufactured using a composite of glass fiber and polyurethane foam. This polyurethane foam is used only in critical areas where the deformation was maximum when we considered de-acceleration forces acting on the shell. Coming on thermal system, uh, since Hyperloop technology incorporates a lot of things which generate a lot of heat, like a propulsion system and braking system, we had to tackle these challenges using a thermal management system. But the key problem with the thermal management system in our cases, uh, in the three-pronged problems are there. First, the amount of heat generated is quite high. We are facing a heat generation level of 15 kilowatt. Further, the area available to us is pretty low. And further, the sink which we have available to discard this heat is just a vacuum, which is a bad sink for the heat. So we had tackled this problem for LIM using a two-phase uh, recirculating system, and for the batteries using a PCM-based system. I'll first like to describe what the PCM system we have to implement for the batteries. We are using paraffin wax. Roughly 10 kgs of paraffin wax is needed for a system to run as per the desired length. Further, for the linear induction motors or the propulsion system, we're using a two-phase immersion cooling, which involves first NOVAC as a recirculating medium, and then water to cool this NOVAC down. NOVAC we are using has a boiling point of 50 degrees Celsius, and it takes up heat from the LIM in the form of latent heat energy and ensures the LIM stays below 60 degrees Celsius of temperature. Once the NOVAC uh, boils off, this boiled vapors are collected, and then these boiled vapor are cooled down using a reduced pressure water. And this water, we can discard it easily in the vacuum. Coming to system level testing, I would like to hand over to Prakhar.
Yeah, sure. All right. So first, let us talk about the propulsion tests. So the way the propulsion tests happen is that we have our disk setup, and this disk, which is the setup that you see on the left, the LIMs are mounted at the bottom. So you might be able to faintly see them. We have the disk, and then on either side of it, we have the LIMs. So in a normal system, the LIM, which is on the pod, would be moving, and the track would be stationary. But in our setup, you can say that the disk is equivalent to the track. Is equivalent to the pod, and that is what moves. And the disk is equivalent to the track, and that's what moves. And the LIM, which is the pod, is actually stationary. It doesn't matter because ultimately the relative motion is what we care about, and it works. It works well for us. So the results from the test setup you can see on the right. These are the oscilloscope readings. The red is the current graph, and the blue is the voltage graph. So yeah, we can move to the next slide. Yes. So the data that we got from the test is as follows. Since this is a no-load test, so our disk is actually very smooth. Because this is a no-load test, the current and the voltage don't exceed very high values. The maximum voltage that we had was 48 per phase, and the peak current was 23 amps. The disk was designed to only go up to 1300 rpm or so. That's why the top speed that we have tested up to is only 1000 rpm, because we don't want to push the limits. The efficiency that we got at this rpm was at the speed was 65%. And attached you can see the graphs for the angular velocity and the acceleration. This was calculated based on the data that we got from the rotary encoder. We can move to the next. Yeah. So now talking about the levitation test setups, we're going to talk about two setups. The first of them is on your screen now. In this, we have again a rotating disc and the EMS below it. So this red holder which you see on the top left image, that's where the EMS goes, and the disc is a separate part of it. The purpose of this setup is to measure the lift force and also the drag force that will be generated while the pod moves along the track. So if you go to the next slide, we can see the results that we have got. Yeah. So again, all these simulations were done on the one slide behind with the results. Yes. So all these simulations were again done on ANSYS Maxwell. You can see the simulated result along with the experimental result. So we basically what we did is we fix for measuring the lift force, we keep the disk stationary, and then we put our EMS below it at a fixed length, and then at a fixed distance, and then the force is measured using load cells. So that's how it works for the stationary test. And then for the test where we need the drag, we rotate the disk, and then we again put the EMF at a fixed point. But this time we attach a rotary a rotary encoder as well. So this gives us the speed after some time, the angular speed after some time, and because of that, we can calculate how much drag uh, the the EMS is producing. So to quickly sum up the results over here, the left ones are, as you can see, they're very good. They match with the experimental results. Sorry, with the simulated data. And on the right, we have a graph which basically just says that as you increase the air gap, the force will reduce, which is again what we expect. So yeah, we can move to the next slide. So this is the second test setup that we are developing. We're working on this right now, in fact. And what this does is this basically restricts the motion of the EMS to just one dimension, to just 1 degree of freedom. So and the reason why this was built is to test the PID controller. As we can see, right, it's an active system. We need an active controller for this. So we plan on testing it for 1 degree of freedom, and then we will scale it up for 3 degrees. Yeah, that's it. So now, Ankit, you can take it back.
Yeah, coming to the suspension test setup. First of all, we are validating the spring constant and damping coefficient using a UTM standard UTM testing. And once these are tested, we are validating the model we have created, the MBD model we have created, using a jig we have created for this testing. In this rig, we have a rails on which we are putting the disturbance blocks, which are moved using a lead screw. And in this testing rig, we can simulate the dynamic condition of our track and see how our spring and damper system is going to behave. Uh, Now, I will just like to showcase how we have integrated all this system into one and showcase how we can test this out. In our campus, we have built a 30-meter track and done the pod run. During this pod run, we were able to achieve a speed of 8 meter per second and acceleration of 0.3 g. This track is quite limited, and we are planning to extend this track further to test more capabilities of our pod. Uh, Now to conclude, I will say the most important part of our development was scalability. And this is the philosophy we have been following throughout the development of our Hyperloop system. To give you a few examples, the decision to go with aluminum as compared to any other material was a compromise between cost and weight we can have. Uh, Further, we have also went with the highly efficient wire bonding technology for our battery system, which ensures our system can be easily scaled up without losing a lot of energy in doing so. I would like to thank everyone for their kind attention. And if you like to more about Avishkar Hyperloop, you can follow us on different social media pages and feel free to contact us anytime you like to. Thank you.
Thank you guys for such a wonderful presentation. We have 5 minutes before we start the next presentation. So any questions that you have? I can see one in the chat box asking, are you guys considering using dielectric coolant?
Dielectric coolant, like I might have not mentioned, but coolant is a dielectric.
Ah, okay.
Novak, we are using Novak, which is a dielectric medium, which has some dielectric capability. And further, we are planning to use with R134 also. For instead of Novak, we might go with R134.